Alright, so we're just doing applications of all of our like exponential and log functions today. So you're given all your formulas here, so and like your test is open note tomorrow, so it's not like you have to memorize them. And we're basically just plugging into this formula, so it shouldn't be too complicated. The first formula that you have is compound interest. So that's very practical because that's like money, banking. You're going to start to do that eventually. So there's your formula for it. So A sub t, or A of t, is the amount in your bank or whatever after however many years. P is your principal, so whatever you start with. R is your interest rate, so you just need to make sure that you're doing that as a decimal. N is the number of times per year that it's compounded, so that'll change just depending on the problem that they give you. And then T is your number of years. You okay with all that? Okay, cool. So we are going to compare the amount of money after 1 year using different compounding periods. So how much money will we have after 1 year if you invest $1,000 at an annual rate of 10%, compounded annually, semi-annually, quarterly, monthly, and daily? So the stuff that's not going to change is how much you start with. So that's our principal is going to be 1,000. So I'll write that somewhere. We'll just say P equals 1,000. Our time is just 1 year, so T is going to be 1 every time. Your rate was 10%, so how would you write that as a decimal? 0.10. And then the N values are going to change. So if it's annually, how many times a year would that be? 1. So we're going to do it when N equals 1. And then semi-annually, how many times a year is that? 2. So we'll say N equals 2. What if it's quarterly? 4, right? Quarters means 4. Monthly? And daily. 365. That okay? Questions? What do you mean? So you're using that formula, and we're going to plug in these values, and then we'll plug in these values, and then we'll plug in these. So you're just going to do it 5 times, which we'll do it in the calculator, so you'll just like switch out the numbers. It's not going to be too complicated, I promise. So for the first one, we'll say A equals, so we're trying to figure out how much money we're going to have. We started with 1,000 for our principal. Then we're going to have 1 plus R over N. Our R every time is going to be 0.10. And this time our N is 1. And then your exponent is supposed to be N times T. So T is always 1, and our N is also 1 this time. So we'll have 1 times 1. Is that all right? So we're just plugging into that formula. Is that okay? Questions on anything, where stuff's coming from, where stuff's going? All right, so you can type that straight in your calculator. I'm not going to bother with trying to simplify it at all. Just type it exactly as we have it written. So as you can see, I am writing it exactly as we have it written, even though I know like 1 times 1 is 1 and something divided by 1 is just itself. That's just going to make it a little bit easier when we go change those N values later. So when we type all that in, we get 1,100. Is that okay? So then for the next one, we're plugging in 2 for N instead. So the only thing that's going to change are those N values. So we're still starting with 1,000. And you're still going to have 1 plus 0.10 over your N value is now 2. And then your exponent is going to be 2 times 1. So if you typed it in exactly like we wrote it on our paper, you can just highlight that and then change out your N values, those 1s for 2s. And so we'll get $1,102.50. Okay? Yes or no? So then same thing for your 4. We're just going to switch out those 2's for a 4. Are y'all okay to do the next two on your own? Yeah, we're just switching out the 12 and the 365. Questions on any of those? Alright, so that's how we do compound interest, and that's basically all you need to know. Yeah. So the next one is talking about continuously compounded interest, so your function just changed a little bit there. Instead of having all this stuff on the inside of your parentheses, we're just going to have that E. So we've talked about a little bit before. Your A is still whatever you end up with, P is still your principal, the R is still your rate, and T is still your number of years. So we want to find the amount after 1 year if a principal investment of $1,000 and is invested at an interest rate of 10% per year compounded continuously. So if it's after 1 year, that's your T value. So we can say T equals 1. Your initial investment was $1,000, so that's your P. Your interest rate was 10%, so how would you write that as a decimal? 0.10. Then it's compounded continuously, so we're going to use that. I call it the PERT formula because it's P-E-R-T. That's just how I remember. So yeah, we're going to use that one. So we'll have A equals. P was 1,000. 1, 2, 3. E to the RT, and our R was 0.10, and T was 1. So again, you can just type that straight in your calculator, and you'll get your answer there. And what do we get? I got 1,105.17. What y'all got? Okay, cool. So that's that one. The next part, we want to know what annual rate of interest compounded annually should you seek if you want to double your investment in 5 years. So we don't know what we're starting with, but we want to double it. So it doesn't really matter a whole lot how you set this up. For some people, it makes more sense to put in actual numbers and solve it that way. So you could like pick whatever you want to start with and then double it and put that on the other side. Or you can just use variables. So we want whatever we end up with to be twice what you started with. Does that make sense? So whatever you ended up with, that's that A value. You want it to be twice our principal, so what we started with. So that's how we're going to set it up. It's compounded annually, so we're not using that PERT formula, but we're using the one back up here. So when we set that up, we'll have 2P equals P times 1 plus, we want to know the interest rate, and it's compounded annually. So what is our N value going to be? 1. So it's going to be some rate that we don't know over 1. And then it's going to be 1 times your time, which was 5 years. Is that okay? And right off to the side. N is 1 because it was compounded annually. And then T is 5. We'll go ahead and label all that. Alright, so from there, we can clean it up just a little bit. So we know that R divided by 1 is just what? R, so we'll have 1 plus R inside the parentheses. And then 5 times 1 is just going to give you 5 as your exponent there. So we want to solve for R. What could we do? divide by p, right? That makes sense? So when you divide both sides by p, you're going to get 2 equals 1 plus r to the 5th. Now what? Do what? Yeah, take the 5th root, right? If something is like to whatever exponent, take the root of that to undo it. So we'll do the 5th root of each side. So I'm going to come up here, kind of run out of room. We're going to have the 5th root of 2 equals 1 plus r. So the 5th root of 2 minus 1 would give you r. And you can type that in your calculator. And that'll give us that value for r. And I think we're going to go like 4 decimal places. I can't remember how many it gives you exactly. Do we know how to do the 5th root on your calculator? We'll go 4. So r is 0.1487. And typically they give you that rate as a percent, so let's convert that to a percent, and what would we have? .87%. That all right? Questions? Alrighty, so good on that. We'll move on to the next ones. So at the bottom there is just talking about exponential growth. So there's your formula for it. This n sub 0, some people call that like n naught. I think that's what they say in like physics. So that is whatever, that's your original amounts, whatever you start with. You've still got e to the kt, and k is just your constant that represents your growth rate, and t is still time. So that's that formula, and we're going to go ahead and apply that back here. So when I was typing these, I goofed a little bit, and all this stuff after e should be an exponent. So just think of it that way. So we've got a colony of bacteria. It's growing according to your law of uninhibited growth, according to this function, where all of this stuff is an exponent, where n is measured in grams and t is measured in days. So what would be our initial amount of bacteria? 100, right? It's whatever number is like in front of your e. So that would be 100. What was the growth rate of the bacteria? So that was like, if you look at the formula on the front, that's the number in front of your t, that k value. So for us, it would be that 0.045. And you could convert that to a percent in case they wanted it as a percent, and what would it be? 4.5%. The next part wants you to graph it. We're just going to skip that. Is that okay? You can just graph it in your calculator. So then we want to know the population after 5 days. How would we figure that out? Just plug in 5. So you're going to have 100 e to the 0.045 times 5. And you can type that straight in your calculator. And we'll have our population after 5 days. I went 2 decimal places. Is that okay? So what do we end up getting? Well, so it's talking about population. So typically, if we're talking about population of things, we do like want to round to a whole number, right? Right, but it's measured in grams, not actual bacteria. Does that make sense? So it's measured in grams, so we can just leave it as a decimal. So actually, can we go back to part A up here where it says the initial amount of bacteria? Can we put 100 grams there, just so that we remember this is not 100 bacteria, but 100 grams of bacteria. And then when we plug this in, what do we get out? 125.23. Is that all right? Questions? Is what? Yeah. Basically. They just have different letters in there. That's all. Because they can. But it's all the same function. Yeah. And they all work the same way. So for the next part, it wants to know how long it will take for the population to reach 140. How would you go about figuring that out? Plug it in where? Plug in 140 for n, so it's set it equal to 140. And then we're going to solve. So we've got 100 e to the 0.045 t. So how would we go about solving that? Divide by 100, what do you get? Or 1.4? Is that okay? Then what do you do from there? Natural log, right? Because you got to get rid of those e's. We want to know what t is, so you've got to pull that exponent out. So if you take the natural log of each side, that's going to help here. So we'll do natural log and natural log. So we'll have the natural log of 1.4 equals 0.045 t. Then our last step to get t by itself, divide. So I got 7.48. So in about like 7.5 days, they get what they needed. It would be 240. Questions there? All right, so the next part, what is the doubling time for the population? So if we're doubling, then what do we need to set it equal to? 200, because you started with 100. So we'll do the exact same thing, but we're equal to 200 this time. So what's our first step? Divide by 100, so we'll have 2 equals e to the 0.045 t. And then how do we get rid of that e? Natural log. So we'll have natural log of 2 equals 0.045 times t. And then your last step, divide. So what does t equal? 15.4. And these are both days. Questions on any of this? Alright, cool. So for the next one, we're talking about radioactive decay, and it's basically still your same formula. They've just changed the variables again. And this time, since it's decay, that K value is going to be negative because it's not growing but decaying. So that's basically the only difference. So yeah, it says that traces of burned wood along with ancient stone tools and an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. The half-life of carbon-14 is 5,700 years. So approximately when was the tree cut and burned? So this was a little bit tricky because you kind of got to set up 2 formulas before you can ever start to get what you want. We've got to find that K value first. So to do that, you're going to use the half-life. So we know that half of whatever you started with is going to take 5,007 years to get there. Does that make sense? So you could just say 1/2 equals, if you started with 1, then we could just leave that as a 1 there, e to the 5,700 times k. Do you have questions on setting that up at all? So anytime they tell you the half-life of something, you could set it up like this to find that k value. So half goes here, and then however many years that half-life is would be your exponent. Does that make any sense? Okay. So then we'll solve that kind of the same way that we were doing up top to figure out your k value. So how would we get rid of the e? Natural log, and then we're going to have to divide by the number in front of k. So in your calculator, you can just type natural log of 1/2 over 5,700. That's going to give you your k. And what do we get for k? It's a really small decimal, right? I did 6 decimal places. Is that all right? Questions there? Okay. So now that we know that K value, we can plug in the other information that they gave us, and that'll help us get started there. So there was this much of the original amount left over. So we don't know how much you started with, but you don't really have to know. We can just convert this to a decimal and put it on this side. Is that okay? So whatever percent you were left with, convert it to a decimal, because it would be that much of 1, right? So that will go over there. So we'll change that to 0.0167 equals e to the kt. So we're going to use our K value from over here. And we don't know what T is because we're trying to figure out how long it took to decay to that amount. So much of the same process again. What are we going to do from here? How do we get rid of the E? Natural log. And then divide by the number in front of T. So we'll have T equals so this is what I got. I got 33.8. So we could say about 33,544 years ago, about. Okay? Questions? Alrighty. So the second part wants you to graph the relation between the percentage of carbon-14 remaining in time. We're not going to do like a real serious graph here. We're just going to sketch it. So what's going to happen over time to the amount of carbon-14 left in there? It's going to just rapidly decrease, right? So we know that you're going to start at whatever 100% is and then go down really quickly. And that's an awful drawing, but that's okay. That's all we're going to do for the graph. You could graph this in the calculator if you really, really wanted to, but I'm not concerned about the graphs today. Is that all right? Questions? I'm more concerned that you know how to use the formula, so if you can do that, then we're in good shape. So we're almost done. The next part that we've got is Newton's law of cooling, so that's what this is right here. So you've got some new variables. So your U of T is your temperature. The capital T is your surrounding temperature. You're going to use that twice. The U naught or U sub 0 is your initial temperature. K is still your constant and T is still your time. Yeah. All right. So it says an object is heated to 100 degrees and it is then allowed to cool in a room whose air temperature is 30 degrees Celsius. So if the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees Celsius? So they're giving us like a whole lot of information there, and it's kind of a lot to put together. But so we're saying the temperature of the object is 80 degrees after 5 minutes. So that 80 is like your ending temperature, your U. Does that make any sense? I'm going to put a U there. And in the 5 minutes, that's obviously our time. So when will its temperature be 50 degrees? So again, kind of like we did with the half-life where we had to figure out that K, that's what you're going to have to do here as well. So they're telling you that it takes 5 minutes to cool to this temperature. So how long would it take to cool to this temperature? So we're going to plug all that stuff in. They gave you that it's heated to 100 degrees. So that's your U sub 0 that you were going to start with every time. In a room whose air temperature is 30, so that's your surrounding temperature, your capital T, is that 30? And I think that's going to be everything we need to start solving here. Alright, so we'll have 80 for that U of T equals capital T was 30 plus parentheses U sub 0 was 100 minus our capital T, which was 30 again, times e to the kt, and we don't know what k is, but we know that t is 5, so we'll say 5k. Is that all right? I know it's like really small. So we need to solve this. What should we do first? Any ideas at all? We can do the parentheses. So we know 100 minus 30 is 70. What do we need to do with the 30 right here? Subtract it, so that's going to give us 50 equals 70 e to the 5k. Then what should you do from there? Divide by 70, so we're going to have just 5 over 7 equals e to the 5k. And how do you get rid of that e? Natural log. So we'll end up doing the natural log of 5 over 7 divided by 5 to get that k value. Does that make sense? Are we okay to do that all in one step? Yeah? Okay. So in your calculator, you're typing natural log of 5 over 7, all divided by 5, and that's going to give you your k value. How did I go? I did 1, 2, 3, 4, 5, 6. I did 6 decimals again. So I got negative 0.067294 for our k value. Is that alright? Questions? Okay, so we're going to use that k value to plug back in, and we want to know now when it's 50 degrees. So all of this stuff is going to be the same, but we're going to have a 50 over here instead of 80. Does that make sense? So, and then you're plugging in your k value. So we're going to have 50 equals 30 plus 100 minus 30. Let me just see if I can actually see it. E to the k, which is negative 0.067294 t. We're trying to figure out how long it's going to take to get there now. Questions on setting that up? Alright, so we'll subtract 30 over, and that's going to give us 20. And then we're going to have 70 e to the negative 0.067294 t. So then we'll divide by 70. And then how will we get rid of the e? Natural log. So you're going to be doing the natural log of 2 over 7. It's negative 0.067294 t, and then divide by that k value. I'm not going to write that out, but you can type that in your calculator, and what do we get? (18.62) and this is in minutes. 18.62 minutes. Is that all right? Questions? Alrighty. So that's that one. Then the next part wants us to graph. We're not going to do that. And then part C is to determine the elapsed time before the object is 35 degrees. So you're doing the exact same thing again, but instead of 50, what are we going to put? 35. So I'm going to let you work through that one on your own. And what do we end up getting there? I got 39.22-ish. Is that what we got? Yeah, okay. Do you have questions on any of that stuff? Okay, so that's all we got.